and welcome class to part 2 of chapter 15, where we're in the middle of our discussion of entropy and its place in our understanding of thermodynamics and spontaneous reactions. And in our previous lecture, we introduced what is known as the third law of thermodynamics, and if you noticed, we've skipped over the second law. So that's actually where we are going to start today's lecture, is with an observation of the second law of thermodynamics. All right, so what's a spontaneous reaction? Well, spontaneity has a technical term, just beyond the colloquial term of like, I'm so spontaneous, I'm so random, ha 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 lol. No, spontaneous does have a very technical definition as well that we use in the sciences. A spontaneous process is one, such as a reaction, that occurs without continuous energy input. So reactions that occur spontaneously continue after they have been given their initial spark, all on their own. Now, spontaneous reactions can be slow or they can be quick. So for example, a slow spontaneous process is that of rusting. So long as there is available iron as well as available oxygen and water, the process of rusting, which is a corrosive process, will continue on its own. This is why, people work so hard to make sure that the iron hulls and the iron parts of their cars are protected and sealed off from the oxygen and the water and other environmental factors, because once this rusting process starts, unless you are successfully able to cut off the oxygen and water again, it will continue spontaneously on its own and slowly eat away at, let's say, your car, like what is being illustrated here. Again, spontaneous reactions can also occur quickly. So that a great example of this is combustion. We know that once a fire gets started, it can be very difficult to put out because this reaction blazes forward with incredible speed. In fact, the energy that is being released throughout this process, we can visibly see in the form of light and heat as this reaction continues to progress spontaneously on its own after it has already gotten started. All right, well, the opposite of a spontaneous process is a non-spontaneous process. And I want to be really clear that non-spontaneous is not the same thing as impossible. In fact, there are many naturally occurring non-spontaneous processes, even out, like if you're looking out the window right now. A non-spontaneous process is simply one that requires a continuous energy input in order to keep moving in the forwards direction. For example, photosynthesis is an excellent example of a non-spontaneous process. So photosynthesis is a reaction that occurs out in plants daily, so long as there is continuous light energy coming in from the sun. So a non-spontaneous process is one that can freely occur, we just need to make sure that we have this continuous energy input. Non-spontaneous reactions are oftentimes considered to be the reverse of a spontaneous reaction. And we can think of this in the same way as, let's say, Hess's law with exothermic versus endothermic reactions, right? If a reaction is exothermic in the forwards direction, we can hypothetically reverse the reaction and our enthalpy also ends up getting reversed. In other words, we change the sign and the reverse reaction is an endothermic reaction as a result. Now, the same kind of thing happens with spontaneous reactions. If you reverse a spontaneous reaction on paper, the result is an example of a non-spontaneous reaction. And this is true of photosynthesis as well. We know, as we just said, this is a non-spontaneous process. Plants need continuous light energy in order to process photosynthesis, and photosynthesis in its most simple form can be seen written in this reaction down below, where over the course of photosynthesis, a plant will absorb carbon dioxide from the air and absorb water from the ground. And so long as we have energy coming in, then the reactants here, the CO2 and the H2O, get processed and turned into sugar and oxygen. Now this is how, again, it's a very simple representation. There are a lot of complicated underlying mechanisms in the cells of the plants that also help this reaction to move forward at a relatively quick pace. However, without this continuous source of energy, like let's say you put a plant under a box, you're cutting off the light energy, this plant can't grow. If there's no energy coming in, the carbon dioxide will just remain carbon dioxide and the water will just remain water. The reverse of this photosynthetic reaction is a combustion reaction, which, as we just discussed, is a really great example of a naturally occurring spontaneous process. If you take a lump of sugar and set it on fire, right, you give it that spark, as long as there's still oxygen around, the sugar will continue to caramelize and burn and turn into carbon dioxide and water. So the forwards direction for photosynthesis written here is technically defined as a non-spontaneous process. This doesn't mean it's impossible. However, the reverse process, taking the sugar and recombining it with oxygen, is going to be spontaneous and can occur without continuous energy input. As we continue moving forward in this lecture, we will continue to focus on the spontaneous processes, but kind of keep in the back of your mind again that non-spontaneous is not impossible, and any non-spontaneous process is going to be the reverse of a spontaneous process, at least on paper. All right, so what does the second law of thermodynamics state? Well, the second law states that the entropy of the universe will increase, provided a process that is being observed is spontaneous. In other words, a dispersion of energy must occur if we are observing a spontaneous process. We can represent the second law of thermodynamics in the equation down below. A change in entropy in the universe is going to be equal to the sums of the change in entropy of the system and of the surroundings, and that this sum must be greater than 0, again, if the reaction is spontaneous. This is a big one. So the delta S of the universe can actually be negative if the reaction or process that we are observing is a non-spontaneous process. So something like, for example, photosynthesis would actually have a negative delta S of the universe. So it's a little strange to think of that. The second law of thermodynamics, again at the high school level, is often stated as like the entropy of the universe is always increasing. It's not always increasing, it's just always increasing for spontaneous reactions, things that occur without the constant and continuous need for an input energy. So if your reaction is moving of its own accord after it's gotten started, then yes, the delta S of the entire universe, the entropy of the universe, will increase as a result. All right, so this is what we're going to be focusing on today, though, is just breaking down this second law of thermodynamics and using it to be able to understand what makes a spontaneous reaction versus what makes a non-spontaneous reaction from the entropic point of view. So let's start with the entropy change of the system. We will look at the entropy of the surroundings in a little bit. All right, so if our system is a chemical reaction, the easiest way to find the entropy change of the system is to observe the standard entropy of reaction, which represents the entropy change that takes place under standard conditions for a given reaction. Now, the delta S, not of reaction, we can see here, does actually have a delta, which means that we are observing a change in entropy for a given reaction using the individual entropy values for the products and our reactants over the course of our chemical reaction. So the delta is important when we are observing a change in entropy. The individual products and the individual reactants inside of this equation do not have deltas because they have their own non-relative / absolute entropy values. I just want to point this out. I've had questions about why we have a delta in some cases and why we don't have a delta in others, so I'm just nipping this one in the bud, right? So if there's a delta present, it's because we are looking at a change in entropy over the course of a process occurring or a reaction occurring, but the individual pieces that take place in this process have non-relative and absolute entropy values, which are always going to be positive values. So our deltas may end up being negative, but the individual particles and the individual molecules will have their own non-relative positive entropy values associated with them. All right, so looking at this equation altogether, right, big picture here, what we are looking at is the sum of the entropy of our products, and we're going to subtract out the sum of the entropy of our reactants. This equation hopefully looks familiar to a similar one where we have observed the delta H of reaction was equal to the delta H's of each of the products minus the delta H's of each of the reactants. This equation is literally set up in the exact same way. The N values, so the N of the product as well as the N of the reactant, are not a total number of moles calculated using something like PV is equal to nRT, but rather these are the stoichiometric values or the stoichiometric coefficients inside of a balanced chemical equation. And if you would like to look up at any point these entropy values, you will be able to find them in S0 of the text, or in Appendix 2 of the text, excuse me. All right, so let's observe over the course of today the entropy associated with a reaction we already know is a spontaneous reaction. This equation here represents the corrosion of iron through rusting. So we're taking 4 irons in their solid form, combining them with 3 oxygen gases and turning them into 2 rust particles, also in solid form. So our question is, what is the standard entropy change of the following reaction? We can see each of the entropy values that we need from Appendix 2 has been pulled from Appendix 2 and placed on the slide here. So I'm gonna let you guys get some practice with the equation that we just saw to calculate the entropy values for this chemical equation. All right, welcome back. Let's get some practice with that previous equation to calculate a standard reaction entropy, which is going to be the entropy change of the system. Again, in this class, we consider chemical reactions like 99% of the time to be our systems. So this reaction is going to be our system here. Well, we're going to take the entropy value of our products and subtract out the entropy values of our reactants. First, to start, we're going to have to take the stoichiometric coefficient in front of the rust, place it down here. This is equal to our first N. And we're going to take this and multiply it by the entropy value of the solid rust. Now, something that's really cool here in this table, again, each of these individual values represents the internal entropy of these solids and gases. We can see that iron in solid form has the least entropy of each of these things, which makes total sense. If we observe oxygen gas, we would predict that because it's a gas, it should have greater entropy, and sure enough, we can see that the calculation of its entropy is greater. Similarly, if we compare iron solid to iron oxide solid, because iron oxide has a larger number of particles in the formula, we would expect it also would have a greater entropy compared to iron on its own, and sure enough it does. It's 90, which is greater than 27.2. So each of our previous, each of the previous qualitative assessments that we made at the end of Part 1's lecture can be used here to make sense of the relative values of our entropies. All right, with that tangent aside though, let's take the 90 joules per Kelvin mole and insert it into our equation right here, 90.0 joules per Kelvin mole. Since the iron oxide or rust is our only product, this is going to be the only product we have to insert into this section of the equation. We're going to subtract out the entropy values for each of our reactants. So 4 times the value of iron, since we have a 4 in our chemical equation here. So that's going to be 4 times the 27.2 joules per Kelvin mole. And we're going to add to this 3 times the entropy value for oxygen. So again, because each of these particles has its own internal entropy that's not relative to anything other than absolute zero, oxygen is not going to have an entropy value of 0 like how its enthalpy would be, but rather it has the greatest entropy presented in this table because it is a gas, freely able to move a large number of microstates that can exist within it as a result. All right, so we have our equation now set up. All that's left is to crunch the number, and we find that this reaction actually has a negative change in enthalpy. the total value is negative 543.8 joules per Kelvin mole. Now this is not a mistake. If we observe the setup of our calculation, it makes total sense. We're subtracting out a larger number than that of the iron's entropy. And even aside from crunching numbers, if we observe the reactants versus the products in this case, the reactants have a gas which is very entropic. It has plenty of range of motion, a very large number of positions with which these oxygens can occupy. And we're taking this free-moving gas and condensing it down into a solid. So it makes total sense that we're decreasing our entropy in this reaction. The problem here, again, is we know that this reaction is spontaneous. So how can we find a positive entropy value if the reaction itself has a negative entropy? We can observe the entropy change of the surroundings to answer that question. Again, if we're working with a spontaneous process, the entropy change of the entire universe is going to have to increase. And the universe is not just the system, it's also the surroundings. So for any spontaneous process, like the rusting of iron, if the entropy change of the system is negative, then the entropy change of the surroundings has best be positive to make up that difference. All right, so how we can determine the entropy change of our surroundings, though, is by making a couple of assumptions about the relationship between the surroundings and the system. Right, it's difficult to observe the entirety of the surroundings because the surroundings is by definition everything in the universe that's not the system. So we're going to make a couple of assumptions here, and these assumptions have been demonstrated to be reliable at higher levels of chemistry and mathematics. So we're just taking advantage of the knowledge that calculus can bring us without actually showing the derivations here because they can be fairly complicated. So what we're going to say is that the entropy change of the surroundings is going to be proportional to the negative enthalpy of the system. In other words, we can think of it like this. If our system, this is our system, is undergoing some type of exothermic process where energy is being released into the surroundings, we know that this is being represented in chemistry as a negative delta H. Well, if energy is leaving the system and going into the surroundings, this means that the temperature of the surroundings is going to be increasing, which we also know gives an increase to entropy. Therefore, entropy is going to be proportional to the negative enthalpy. This we can represent in our equation down below, where the delta S of the surroundings is equal to the negative delta H of the system. And because our entropy has an explicit temperature dependence, we're going to say that this enthalpy is divided by T. Units-wise, this makes total sense. Our enthalpies are in joules per mole, oftentimes, or something like kilojoules per mole. We know that entropy, though, is a joule per Kelvin mole. So we need to make sure that we're taking this enthalpy and we are dividing it by a temperature to make sure that the temperature dependence of our entropy is also present here. So if we know our system, we can find the entropy change of our system using the previous equation. If we also know our system, though, we can find the enthalpy of our system and in combination with the temperature, calculate the total entropy change of the surroundings. And again, this relationship, we're not working through the hard and heavy math to prove its legitimacy, but I am asking you through this qualitative description here on the left to trust this equation. Because of the first law of thermodynamics, all of the energy that's moving from systems to surroundings is going to be conserved, and the relationship between our enthalpy and our entropy can be trusted because of the first law of thermodynamics in combination with our second law. Okay, so we found the entropy change of the system for the rusting of iron. So let's now observe the entropy change of the surroundings in this process as the reaction is fairly exothermic, we can see its enthalpy being given down below. We know because it's exothermic, it will be giving heat and raising the temperature of the surroundings. What we're going to do then is observe how this exothermic reaction is going to impact the entropy of the surroundings as a result, and therefore is also going to impact the entropy change of the entire universe. So now that you have the equation that you need to find the entropy of our surroundings, please calculate that as well as the entropy change of the entire universe for the rusting of iron. All right, so let's come back together, calculate what the entropy change of our surroundings is going to look like, what it's going to be. So the entropy change of our surroundings is equal to the negative enthalpy change of the system, all divided by T. Now the tricks here are going to be obviously observing the units to make sure that everything is going to be is going to work out, not just with the entropy change of the surroundings, but also that of the universe. So if we plug our enthalpy of the reaction in here, a negative of a negative 1648 kilojoules per mole, we will then take that and divide it by our temperature. Now the temperature here is explicitly given in degrees Celsius. However, as was previously stated, the units of our entropy are in a per Kelvin unit. So we do want to make sure that we convert this temperature out of 25 degrees Celsius and into 298.15 Kelvin. This temperature is going to be the temperature that we insert into our equation here. So we're taking our 1648, dividing it by 298, and this gives us an entropy change of the surroundings equal to 5.53 kilojoules per mole Kelvin. So we can see that the entropy change of the surroundings is definitely positive here, and again it's positive because we are increasing the temperature of the surroundings via this exothermic reaction. So our final question is, was that enough? Is increasing the entropy of the surroundings enough of a driving force to really make sure that this reaction is spontaneous? To answer that, we will calculate the entropy of the entire universe by summing together the entropy of the system and that of the surroundings. If the sum of the systems and surroundings is positive, this means that we are working with a spontaneous reaction. Well, the entropy change of the system, we found already, it was equal to negative 543.8 joules per Kelvin mole, and I'm just going to convert that into kilojoules right away. So again, we need to make sure that our units are working together. So if we convert that to kilojoules, we are actually working with a negative 0.5438 kilojoules per mole Kelvin. See, again, I said we have to make sure that we're paying attention to our units, because if we're not, we would have drawn the wrong conclusion about this reaction. If we're working in kilojoules, then our entropy of the surroundings we can also see above. I'm just going to do a down arrow like that to insert that number, so I actually have space to write the total entropy change of the universe. So if we're taking 5.53 and subtracting out 0.5438, what we find is a total entropy change of the universe equal to 4.98 kilojoules per Kelvin mole. I realize that I keep writing sometimes mole Kelvin and other times Kelvin mole. The two can be interchanged, that's fine. The point here is that the entropy change of the entire universe as this reaction is undergone is positive. What this signifies is that the entropy change of the surroundings and its positivity is enough of a driving force for this reaction to continue spontaneously. Even though we're taking gaseous oxygen and trapping it inside of a crystal, the amount of heat that is released in this reaction through the enthalpy is enough to drive the reaction to completion spontaneously without consistent energetic input. All right, so that is though the connection between the entropy and the enthalpy of a reaction. This is the trade-off that we're constantly trying to observe. Is the reaction stabilizing enthalpically as energy is being released via an exothermic reaction like we can see here? Is it stable entropically, as reactants could be turned into a greater number of products? Or is there going to be a competition between the two? And if so, which is going to win? As it turns out in the rusting of iron here, again, we can see that the entropy change of the surroundings is enough of a driving force to make sure that this reaction moves forward spontaneously. If, however, the enthalpy or entropy change of the universe would have been negative, we would have concluded that this is a non-spontaneous reaction and requires continuous energy input to proceed. All right, well, I think observing the energy changes, the entropy changes of the systems and surroundings, as well as that of the entire universe, is enough for one day. So, if you have any questions on entropy thus far, as well as the entropy changes of the universe, please do not hesitate to let me know. If you have any homework, please double check and do your homework, and until next time, class is dismissed.